All right, so this is the coding part of the simple linear regression from scratch. This is going to be the actual from scratch part. So I have from scratch in the PowerPoint, I had it in quotation because nothing is ever really from scratch. I'm still using Python, I'm still using NumPy, Pandas, Matplotlib, but I am not using scikit-learn. I'm not using any machine learning modeling package. We're going to try to do this go through the reasoning ourselves without using any kind of easily importable package. So, having said that, we are using pandas, so go ahead and import that. I'm not going to go over what this is. I assume you guys know a little bit about pandas. We're just reading in this data file, which comes from Kaggle. I think it's used a lot. It's just a really simple salary data set. It has as a Y variable or a target variable, it just has salary in USD, and then as it has a single predictor, and that is years experience. So you can go, let's hold on, let me just make sure this is working. Okay, great. Yeah, so here's just the header for the data file. So years experience, time, that's going to be our predictor variable, and then salary, you don't see it here, but it's in USD. So this is how much you make annually. And we want to see if there's a relationship between those, and we want to see if we can map the line best fit, again, without using any scikit-learn. So let's go down here. I'm just going to put these into NumPy arrays in case I need it. All right, so this is just visualizing the entire data set. Looks pretty linear. I don't think anyone would dispute that. I hope that years experience and salary are at least correlated. I didn't know if in certain domains they might not be linear. There might be something more like a polynomial relationship where you reach a certain point and there's a massive spike in salary. But this looks pretty linear to me. So going back to residuals here, again, we want to fit a line to this. What line are we going to choose, right? We know that the MSE is going to be our loss function. That's how we evaluate the legitimacy of our line by trying to minimize the mean squared error. But again, how do we figure out M and B? How do we know if a line is defined as y equals mx plus b? How do we know M and B, right? Are we just going to pick randomly and then sort of adjust it like a sort of hyperparameter tuning? Well, that's what I'm going to do at first. I'm going to show you that you don't actually have to do it that way, but I'm going to do it the hard way first. This is just a plot showing residuals. Again, we want to minimize these. The residuals, again, we're going to take actually the square residuals. So for every single x, we have a predicted value in accordance to this red line. And then there's going to be a corresponding actual value. You take the difference between those, square them, add them all up, divide by the number of observations. That's going to give you the MSE, and we want to minimize that. Ultimately, we want to just find the line that has the least amount of squared residuals. So we're going to do it the hard way. Yeah, and again, I'm just showing MSE. This is all a review. Please watch the previous video before you watch this. Yeah, so we're going to talk about this, the least squared method, but first we're actually going to do things by eye. So I, right here, just created a line by eyeballing it. So I said from 1 to 10 years, these are the x coordinates. I said at 1 year, you make about $30,000 according to this data set. And then at 10 years, you make about $120,000. So then create a line using these. And honestly, it looks pretty good. I've done no math there. I just eyeballed it and said, and I could go in and figure out the MSE, and then I could kind of adjust it like that. And honestly, some machine learning algorithms kind of follow this line of reasoning because they don't have, and you'll see later later on, they don't have a neatly solvable loss function. But lucky for us, simple linear regression does. The MSC does. Now again, you can use other loss functions with linear regression. You could use MAE, which is instead of taking the squared residuals, you take the absolute residuals, so the absolute values of these residuals. So instead, in this formula, instead of a square, you could just have an absolute value. You can do that. But again, the overwhelmingly popular one is going to be the MSE, the mean squared error. So I also made a couple of lines right here using the exact same x coordinates and just different y coordinates. So the one I had first was, I said at year 1 you make about $30,000, at year 10 you make about $120,000. This one says you make about $20,000 at year 1 and then $130,000, so on and so forth. I've made these lines like this. So then we're just going to go ahead and plot these lines, all different colors. Let me just like zoom in a little bit. All right, so this is just eyeballing it, and this is kind of a mess, but again, some machine learning optimization follows this logic where you kind of have to just eyeball things and then hopefully things are falling into place, especially stuff like hyperparameter tuning. But for simple linear regression, we don't need to do this. Luckily, there is a very elegant, solvable solution. We don't have to do any of this eyeballing, but I'm sort of showing you the reasoning behind this. So let's say we took all these lines, right, and then we calculated the squared residual, the sum of squared residuals. So that's each one of these lines here, say this purple line, this is going to have certain residuals and you're going to sum them all up. That's going to be different from, say, this green line. It's going to have different residuals as opposed to the red line, etc. So let's just do that for just demonstration's sake. Again, we don't have to do it like this, but I think it's good to see the sort of reasoning behind it. Because really, all of these are going to follow the same loss function to evaluate, right? So for right here, go back up to our MSC. See this y hat sub I? This is where we put in our mx plus b. We're just changing m and b, right? So if you can think about this as a multivariable equation where you know your y sub I, this is all the predictions that you're taking. And then in your y hat sub I, you have mx plus b. Well, you know your x, you know your n, that's just the number of observations. So really all you have is just m and b. So that's going to give you a function. It's actually going to be a three-dimensional function for simple linear regression. For multilinear regression, it's going to be more and more dimensions, but for the simplest thing, and I'll show that later on, you're going to have a 3D model, a 3D function where MSE is dependent on how you're changing m and b. Again, m and b is the mx plus b that this y hat sub I represents. So as we change all of these, all we're doing down here is we're just changing m and b. We're changing the intercept and we're changing the slope, and we're getting a single value, an MSE for that. And we can actually plot that value with respect. And what I'm going to do is I'm going to keep, because we're going to look at 2D graphs, I'm going to keep that value. I'm going to keep the intercept constant and just change m. But in reality, you would be changing both. So right here, we're just going to set b equal to 20,000. And then here, we're going to calculate the slope based on that first line. And then we can, so we can create a series of lines based on the slopes that I defined up here on this thing. Okay, so that's what I'm doing here. And right here, you're going to have, for each one of these, you're going to have a predicted value, right? So the year's experience is X. There's line 1, line 2, line 3, 4, 5. For each one of these, there's a different M and B, which we calculated up here. And again, we just kind of pick these randomly based on eyeballing. So for each one of these, there's going to be a prediction. Now we know the actual, again, we're treating this whole thing like it's training data. And so then what we can do is we can calculate the residual from that, which is right here. And we can actually, I squared the residual too. So we're going to do the square residual for every single point, for every single line. And if we add all of them up and divide by the number of observations, we get the MSE. Right here it says sum square residual. Really it should be the mean, the MSE. But again, we're kind of all measuring the same thing. If you don't, you could do just sum of squared residual or MSE. The point is we're not actually calculating anything here. I'm just trying to demonstrate this. So again, we have 5 different lines that I just created by eyeballing. Each one of those has their own slope, and I actually made all their intercepts the same. So they're a little different from this. Imagine all these, but they have the same intercept, just at slightly different angles. And then I made a prediction based on that equation. I know the actual value. I get the residual of that. I square that. I add that all up for each line. So each line's going to get a single value for the sum of squared residuals, right? Because it's all of these entries added up. And then I just divided by the number of entries because that is how MSE is set up. You can do it either way. If you don't want to divide by it for this, you don't have to. All right, so let's just make sure this is working. There we go. That seems to be working. Okay, cool. Just make sure that's that. Okay. So now what I'm going to do is I'm going to plot all of these. Remember, we made the intercept the same for all 5 of these lines. We should have 5 points, 5 MSCs, 1 for each line, and then a corresponding slope, one that we had established earlier. So here you can see that as the slope is changing, the MSE is also changing, and it almost looks like a parabola with a local minima around 10,000. 10,000 was actually the slope that we had originally eyeballed. So this looks pretty close to actually where it is. So in reality, you would have multiple parabolas like this because you would also be changing the intercept. So you're changing the slope and changing the intercept. So you get something that actually looks more like, go back here, like this. And again, this says root sum of squares, residuals. That is if you took all of the squared residuals, sum them, and then square rooted that. So again, we're measuring different things. You're going to have the MSC, you're going to have, but the point is you have some value that's supposed to represent all the residuals added up in some way, and they're squared. You have to make sure that before you add them up, you square them. That's very important, unless you're doing an absolute value loss function, but you have some metric. This is how we're evaluating the line best fit, and B or beta sub 0, beta naught, that is the intercept in our y equals mx plus b, that would be b, and beta sub 1, that is our slope for our single predictor variable. So that's just our slope. So you can see that as these are changing here, the corresponding sum of squares is going to be changing as well. And what you're looking for is you're looking for this minimum. This minimum is going to be the lowest possible squared error that you get given a linear model. And for simple linear regression, when you have a single variable, it's a very easy equation. It's also easy when you have multiple linear regression, but it's even easier when you just have a single predictor variable. And what you get is this, or the least squares method. Basically, okay, so we know about derivatives. If you take a derivative you can get of this function, this MSE function or RSS function or just squared error function, you can get the local minimum by figuring out where the derivative is equal to 0. And going back to our MSC, I'm not going to go through it because it's actually a lot of derivations and things. If you go to these, let's go back up here, and you plug in mx plus b, and you take the whole derivative of this thing. You have to use the chain rule, right? Because you're going to have multiple things embedded, multiple functions embedded in one another. But if you go through all that, ultimately you get something very elegant that looks like this. And so this is the reasoning behind this. So luckily we don't have to just pick a bunch of stuff and eyeball them and then measure it. We actually know that no matter what, taking the derivative of this function, this MSE, when we plug in a linear equation into the I hat sub I, you're going to get this very elegant equation where m, that's our, and everyone uses different symbols for everything. It's very confusing. But m here is the slope. Here you have I sub I, that's just the, or excuse me, x sub I, that's just the x value for any given instance, minus x bar, which is just the average of all the x's, times this difference, which is y sub I. Y is just any value for the predictor or target variable, excuse me, minus y bar, which is the average for all the target variables. Then you multiply these by each other, the differences by each other, sum them all up, and that's in the numerator. In the denominator, you're going to just take this function, and instead of multiplying it by the y difference, you're going to square it, add those all up, and then ultimately you just divide the numerator by the denominator, you get your slope. You can plug in your slope here. This is again just the average y minus the slope times the average x. This will give you the intercept. So this is an extremely elegant equation that your computer is just doing like that. It doesn't have to. So, I mean, you've probably heard of gradient descent, where you take something like this. This is if there wasn't a single minima here, a nice little 3D parabolic function. If instead there was all sorts of crazy humps and minima and stuff like in all sorts of different loss functions, then you would have to search, and that is exactly what gradient descent is. It is trying to find these minima by searching and changing these parameters, and that is an entire, there's all sorts of different approaches to that. There's no one size fits all, but luckily for simple linear regression and multiple linear regression, there is a very nice parabola when looking at the loss function that has a very elegant solution when you take the first derivative of it. All right, so let's see if we can apply this to our equation. We're going to apply this least squared method. Again, we got that from taking the derivative of the MSE when we place the mx plus b inside. And let's see what we get. All right, so this is doing all of these. This is doing all of this right here. Calculating that, and then we're going to, so the slope of the line best fit is 9,449. So we had originally said 10,000 when we eyeballed it. So we're actually pretty close. We're off by about 5,000, but that's not a lot in the context of these big numbers. And then C is, all right, so C is around 24,000. So we had said that it seemed like with 0 years, if you were just an entry level, you'd be getting paid about 20,000 to 30,000. So this is saying you get paid around $24,848 annually. That's pretty close. And let's see the line best fit right here. This is what it looks like. So actually pretty I mean, this was such a straightforward linear. So this is just me eyeballing it. And then this is after doing all these calculations. This is the line best fit right here. So it's actually pretty close. But again, this is going to be even better than eyeballing it. And a lot of times you're not going to be able to eyeball it at all because it's not going to be extremely linear like this. We can get the RMSC. This is, again, this is the root mean squared error. So this is our mean squared error, and we just take the square root of all that thing. So it's back in the units of the original target variable, right? So this is just saying on average the squared residual is around the residual is around 5,000, and when you're with big numbers like that, that's not that bad when you're looking at tens and thousands of dollars. So I know we said we're not going to use scikit-learn, but I just want to import it right now because I want to compare what scikit-learn's linear regression model does with what we just did. So I'm going to get that in. I'm going to import it. Sorry, my computer's being really slow. All right. So here, I'm sure you know all about NumPy, and we're just going to go ahead and going to fit the model to this. Exact same data. Okay, cool. We got that. And then we're going to actually just look at the coefficients and compare the two. So we are off by 3.6 times e to the negative 10. So that's a pretty percent. Okay, so that's actually our coefficients are very, very close. We're off by about 1/1,000,000th. Let's look at how our intercepts differ. Again, really, really small amount. And then let's compare the RMSC of the two models. So again, I'm comparing the scikit-learn with my model. Let's see. Oh yeah, you have to import mean squared error separately with scikit-learn. But again, this is not about scikit-learn. So, all right, so we are again off. We basically had the exact same. Let's just look at them all. So right here, this final thing is the table between our from scratch and the scikit-learn. So these are our coefficients. Simple linear regression, this is a single coefficient. So they had a little more granularity than us, but we basically got the same thing. Intercept, exactly the same, it looks like, yep. And then the RMSC was exactly the same. So as you can see, we were able to do the scikit-learn is just doing the same thing as us. It's just doing the least squares methods. But it's nice to be able to go in and know exactly what we're doing so that way we have a way better understanding of what's actually going on. All right, well, thank you so much. That's the end of this video.